In your geometry class, you learned that if you have two triangles that have two angles that are congruent, or two pairs of angles that are congruent, I should say, so angle and another angle, and one other side then these two triangles absolutely positively have to be congruent. We call that the angle side congruency. And by the way, it also would have worked if the second angle we had was this one right here. We call that the angle side angle congruency. You learned in geometry that those congruencies work. That as long as you can prove that two triangles have these three matching pairs of measurements, the two triangles have to be exactly the same. It means that the unknown third angle have to match, which makes sense because in a triangle, if any two, we can always find the third angle by subtracting the first two from 180. So if we know that two triangles have the same first two angles, they have to have the same third angle also. That makes sense. But also that the other two sides have to match. There's no way around that. Absolutely have to match. That's what it means to say that there's an angle side congruency. And here's why. The law of sines tells us that as long as we have one angle side pair, in this case that would be angle side pair, then if you're given another measurement, like the other angle, you can find the other three measures of the triangle, which means since you can find the other three measures of the triangle, you'd get the same answer every time. Which means as long as you start with that angle side, every single time you're given the same angle side pair, you're going to end up with the same answer in the end, the same 6 measurements, the same exact triangle. So let's see how that works. This was from your video notes. So we're just going to walk through this process, and hopefully you can keep up. So first things first, if you're given two angles in a triangle, you can find the third easily. Remember, that was the first thing on our list the other day. If you ever have an 80-degree angle and a 45-degree angle in a triangle, you can always subtract from 180 to get the third angle. And something important that I forgot to mention first is that when you set up this box, so what I want you to do is get used to setting up this box where you kind of put all of 6 measurements of the triangle, sort it with the known numbers, the known measurements on the left and the unknown on the right. The order you do it in doesn't matter so much, but just known on the left, unknown on the right. The first thing we're going to find, we'll go on top here. We find this 55-degree angle first. And so now we can keep moving. We can do the harder stuff. And I'm going to use the law of sines to find the missing side length. And remember, the key here, the tip-off that I was going to use the law of sines, is that I have an angle side pair. As long as I have angle C and side C, I can do a pair. So I can use 3 over the sine of 80 degrees to find my missing pair. I can start with B over the sine of 45 degrees. And notice how I use the version of the law of sines with the sides on the top, because I'm looking for a missing side. It's convenient if that's in the numerator. Well, to get B by itself here, all I need to do is multiply both sides by the sine of 45 degrees. So that's 3 times the sine of 45 degrees over the sine of 80 degrees. And that is as simplified an answer as I can get. If I want to approximate, which we almost always do when we're dealing with triangles here, I would need to turn to the calculator for that. And with Desmos, every time you open a new Desmos, it opens in radian mode, and we want it in degree mode. So get in the habit of always making that switch if we're going to look for the sine of degrees. And I can just type in 3 times the sine of 45 degrees divided by the sine of 80 degrees, and that is my next side, is 2.15. Ordinarily, you're fine rounding to the nearest tenth in your final answer, so I'll call this 2.2. And then we'll do the same thing to find the other side. Because 2.2 is a rounded answer, I'm not going to use my rounded answer to then turn around and try and find another one. I'm going to stick with my exact measurements. 3 over the sine of 80 degrees equals the other missing side divided by the sine of the corresponding angle. And so A equals 3 times the sine of 55 degrees over the sine of 80 degrees. And so I'll go back to my Desmos. And, well, this one, I can just change that 45 to a 55. And so my other side is 2.495, which we will call, in our answer box, we will call that 2.5. Going back to our triangle congruencies for a minute. There we go. We learned that some triangle congruencies don't work. In fact, there's one in particular. And that was angle side side. Your geometry teacher probably made some corny joke about the naughty word. And you remembered that angle side side is not a way to prove triangles are congruent. So if these two triangles have the same angle right here, and then the two sides that don't surround that angle, so this pair, and then this pair, these two triangles are not necessarily congruent. And in the rest of this video, we'll see an example where they are congruent, where you can find the missing piece. And then in our next video, we'll talk about why that's not good enough. So let's take a look at this angle side side example. We're given the 105 degree angle here, and then the 6 and the 9. And we're going to find that there's only one way that the rest of the triangle can be filled in. So if I ever give you another triangle that has 105 degrees, 6, and then 9, it's going to have to be a congruent triangle. Exact same measurements. Again, I want you to start by making that box with the known quantities on the left and the unknown ones on the right. So we'll fill that in. We know that angle A is 105 degrees. We know that side A, the one across from it, is 9, and side B is 6, because that's across from the angle B. What we don't know is angle B, but we're going to find that first, because if we look at the information they gave us, we can see we have the angle side pair, A and A. So we can use sine of 105 degrees over 9 is equal to the sine of angle B over 6. And notice how this time I put the angles on top, because I'm going to be wanting to find an angle, so it belongs in the numerator. And so we're going to cross multiply here. The sine of angle B, or not even cross multiplying, just multiply both sides by 6, is equal to 6 times the sine of 105 degrees over 9. And, well, what do we do next? I'm telling you that the sine of angle B is equal to some weird fraction. I don't know what it is. If it helps, you can certainly go to Desmos and just type that in to see what it looks like. It was 6 times the sine of 105 degrees over 9. So 0.643950, etc. So what I'm saying is that angle B has a sign that is equal to that decimal. I need to then figure out what the angle is. And we saw this last week when we were looking at right triangles, and I gave you two sides of a right triangle, and we said, oh, well, that means that the sine, we could use the opposite over hypotenuse to figure out what the decimal or the fraction is, that is the sine of that angle. And then in order to find out what the angle is itself, we can use the inverse of sine, or what we call the arc sine. And this gets back to the idea of an inverse that we spoke about last week. If you know that the sine of some angle is equal to this decimal, the whole point of inverse functions is to take that decimal and turn it back into the sine. So if I find the arc sine of that decimal, which I don't really want to type the rounded number in, I want to type it in exactly like that, the arc sine of that will give me angle B. And again, I'm using Desmos for that. What's nice here is I can just I already have this typed in, so I can just ask for the arc sine of that. And it is 40.087, which I'll just call 40 degrees. Generally speaking, we will be rounding degrees to the nearest whole number, not decimals, because degrees are already very small. There's very, very, very tiny difference between 40.1 and 40.2 degrees. So we're just going to call it 40 degrees. And so now that I know that, I can move on through the rest of my pieces. It helps, by the way, if you then put that 40 degrees in here. And then I can say that my third angle, this is the number one underlying thing we said first when we looked at triangles. If you know two angles, you can find the third. So 105 degrees minus, 180 degrees minus 105 degrees minus 40 degrees is equal to C. And so something that's cool is I don't really want to use a rounded number of 40 degrees. So something that's cool, I can do this either on the calculator or on Desmos, is I can call that B. And now every time I use the number B, it's going to remember that number. So if I want to do 180 minus 105, instead of typing minus 40 point blah, 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 I'll just do minus B. And so that gives me my angle C, 34.9 degrees, which in my answer box, it's completely fine if I round that up to 40 degrees. Sorry, to 35 degrees. But I don't want to use that in my calculations. So what I'm going to do is back in Desmos, I'm going to call this angle C. And so then I can use my law of sines again to find the third side, the only missing piece that we have left. Going back to my original law of sines, side A divided by the sine of angle A is equal to side C, which I don't know, divided by the sine of angle C. Now, I can write down 34.9 in here if I want. But when I do my math on Desmos, instead of typing in the sine of 34.9, which is a rounded number, also kind of annoying to type in, it's a little bit easier if I just go to Desmos and I use that C. So I can say 9 times the sine of C divided by the sine of 105, which was exact, and that gives me 5.332, which in my answer box I'll just call 5.3. And I do want to make sure we have this summary down that anytime you're looking for a missing angle using the law of sines, you are going to have to use inverse trig. And in this case, that inverse trig is arc sine. So make sure you're kind of ready for that. Okay. In our next video, we're going to take a look at some examples of an angle side-side setup that don't quite work. And you'll see why your geometry teacher wasn't just messing with you, they were actually right about triangle